Today we're going to be talking about section 5.3 in your textbook, Diagonalization. So in our previous video, we were talking about finding eigenvalues. And we had a whole system for doing this by finding the characteristic polynomial, setting it equal to 0, and solving for those eigenvalues. Today we're going to be talking about a shortcut for doing that. So let's start off with the definition. This definition is actually from section 5.2, but I found that it was more relevant for this section. So A and B, if they're square matrices, they are called similar if there exists an invertible matrix P such that A equals PBP inverse. What this basically means is we can take A and we can factor it into a product of three separate matrices, where the matrices on either side are inverses of each other. And we actually saw an example of this in your practice exam. What we showed in your practice exam is that if we take the determinant of PBP inverse, that's going to equal to the same thing as the determinant of B. And that's what's going to be key in making all of this useful. So because the determinants, in this case, if A and B are similar, because the determinants are the same, that means that they're going to have the same characteristic polynomial. So that means they'll have the same eigenvalues with the same multiplicities. And this is really, really helpful if we have a matrix that looks complicated. If we can turn it into, or if it's similar to a matrix that is simpler, then we can find the eigenvalues of the simpler matrix instead. So that's going to be our goal. In particular, we're going to try to see if we can make A be similar to a diagonal matrix, a matrix that just has entries on the diagonals and zeros everywhere else. If A is similar to a diagonal matrix, then we can just read the eigenvalues of A straight off of D's diagonal entries. So that's going to be our goal for this class. It's called diagonalization. Before we get into eigenvalues, let's see what else we can do with diagonalizable matrices. So if A is diagonalizable, so again, we can factor it into PDP inverse, where P is a diagonal matrix, then it's really easy to calculate the powers of A. So for instance, let's try out a couple of smaller powers. So let's say we want to find A squared. Well, A squared is just A times A, and A is PDP inverse. Right, so A squared is just going to be PDP inverse times PDP inverse. But you'll notice that now we have a P inverse and a P right next to each other. So those are going to cancel out, and that's going to leave us with PDDP inverse, or PD squared P inverse. Similarly, if we did A cubed, this is the same thing as A times A squared. So PDP inverse times A squared, which we already calculated to be PD squared P inverse. And again, in the middle here, we've got a P inverse times a P. Those are just going to cancel out, leaving us with PD cubed P inverse. And we can keep doing this sort of indefinitely to get any power of A that we want to. So A to the K, for whatever K we want, is going to be D to the K P inverse. Why is that nice? Well, that's nice because it's really, really easy to take powers of a diagonal matrix. So with a regular matrix, if we wanted to take a power, we'd have to multiply it by itself that many times. But with a diagonal matrix, all we have to do is take the powers of each diagonal entry. And those are real numbers. That's really easy to do. So I can take every single diagonal entry, raise it to the kth power, and zeros everywhere else, and that's going to be D to the K. So what this means is if A is diagonalizable, it becomes super easy to raise A to a power. And this is really helpful in a lot of applications. For instance, some of you might have heard of Markov chains. This is a way to model time series data, so like the stock market or things like this. This would be really helpful to be able to raise to a power. That shows us what happens over time. Let's take a look at an example. So this is problem 4 from section 5.3, and it says we're given this factorization. So A is diagonalizable, and in fact, they found the diagonal factorization for us already. And it wants us to compute A to the K for some arbitrary K. So let's do it. A to the K, we already decided was going to equal to P D to the K P inverse, which is equal to, here's our P. d to the k, all we have to do is raise each of these diagonal entries to the k, and then times p inverse. So let's go ahead and multiply that out. Now we have 3 matrices to multiply, so we'll start by multiplying the rightmost 2. So I'll leave this leftmost matrix alone for right now. And if I've got, I'm multiplying these rightmost 2 matrices, so I've got 2 to the k times negative 1 plus 0 times 1, so that's negative 2 to the k. And then in our upper right corner, we've got 2 to the k times 4 plus 0 times negative 3, so it's just 4 times 2 to the k. And then in our bottom corner, we've got minus 1 times 0 plus 1 to the k times 1. 1 to the k is, of course, just 1, so here's just 1. And then we've got 4 times 0 plus 1 times negative 3, so it's just negative 3. And then we can multiply and get our leftmost matrix in. So we've got 3 times negative 2 to the k, so it's negative 3 times 2 to the k, plus 4 times 1. And then our upper right, we've got 12 times 2 to the k, that's 3 times 4 times 2 to the k, minus 4 times 3, so minus 12. In our lower left, we've got minus 2 to the k times 1 plus 1 times 1. And in our lower right, we have 4 times 2 to the k minus 3 times 1. Okay, so here's our matrix. It was a little bit of work to figure out, but all we actually had to do was multiply 3 matrices. Now, if k were some big number like 100, if we wanted to find a to the 100, we would have to multiply a times itself 100 times. That's 100 multiplications. As opposed to finding a to the 100 using diagonalization, we literally already did that. We would just have to plug in 100 for k and we're done. So this is one example of how diagonalization is super, super helpful. Okay. Let's go back to what we were originally hoping to talk about, which was eigenvalues. So this theorem is going to be our very powerful theorem for this section, the diagonalization theorem. So a matrix A is diagonalizable, so we can factor it into those pieces, if and only if the columns of P are n linearly independent eigenvectors of A. Now, they have to be linearly independent or P won't be invertible. But we can build P by using eigenvectors of A. And if we do that, then the diagonal entries of D are going to be the eigenvalues of A. So P is made of eigenvectors, D is made of eigenvalues, which is super helpful because that means if we can factor our A out into a diagonalizable form, then we can just not only read off eigenvalues, but also read off eigenvectors. So let's take a look at this in action. So this is problem 6 from section 5.3, and it has an already factored out matrix A, and it's asking us to find the eigenvalues of A and find a basis for each eigenspace. That's another way of saying find us linearly independent eigenvectors, right? Because if we have linearly independent eigenvectors that match the dimension, then they automatically also span. And so they're a basis. This is the basis theorem from section something, 2.9, I think. All right, so let's start with the eigenvalues. We read the eigenvalues off of D. D has 3 spots, but only 2 of them are distinct. So we have eigenvalues 5 and 4. Because 5 has a multiplicity of 2, there are 2 copies of 5. This means that the eigenspace we're hoping is going to be dimension 2. So let's start with the basis for the eigenspace associated with lambda equals 5. Well, we saw in the diagonalization theorem that the entries of D are the eigenvalues that correspond respectively to the eigenvectors in P. That means that since 5 shows up as the eigenvalue in the first 2 columns of D, then the corresponding eigenvectors are going to be the first 2 columns in P. So, and because they're linearly independent, that means they're going to make a basis. So our eigenspace, here's our first column of P that is associated with 5, And here's our second column of P, which is also associated with 5. So here's our basis for our eigenspace. If we want to look at the basis for the eigenspace associated with 4, then we see that 4 is in the third column of D, so the third column of P should be our eigenvector for that. So that's -1, 2, 0. So the diagonalization theorem has a lot of words, but it's very easy to implement. All we do is we say the eigenvalues are what's on D, and whatever columns the eigenvalues are on, those corresponding columns in P are going to be eigenvectors of that. And in fact, linearly independent eigenvectors. Okay, so we just saw why it's helpful to have A be diagonalized. And once we are able to factor A into its diagonalization, how we use that to find eigenvalues and eigenvectors. So now let's talk about how do we actually diagonalize A. So in order to diagonalize A, we want to find P and we want to find D, right? So we're going to start with finding the eigenvalues of A, and then we'll find n linearly independent eigenvectors of A. And how do we make sure they're linearly independent? We'll just take basis vectors for each eigenspace. If we can't find n linearly independent eigenvectors, that means A is not diagonalizable. Once we've found those eigenvectors, we can use those to build P, and then we can build D from the eigenvalues. And the important thing here is we need to make sure that we're building D from the corresponding eigenvalues. We need to make sure that the eigenvectors that come from each specific eigenvalue are in the same order as the eigenvalues are. So let's actually see how this works. So this is problem 10 from section 5.3, and it's just asking us to diagonalize A. So what this means is we want to find our P and we want to find our D. So let's start off by finding the eigenvalues. That's our first step. And we find the eigenvalues, this was from the last video, by finding the characteristic polynomial, which was just the determinant of A minus lambda I. So this was 2 minus lambda, 3, 4, 1 minus lambda. So this matrix that I just wrote down is A minus lambda I. So we want to find the determinant of this. And so we multiply the on-diagonal entries, and then we subtract off the off-diagonal entries. So this is going to give us 2 minus 3 lambda plus lambda squared minus 12. So that means that our characteristic polynomial is lambda squared minus 3 lambda minus 10. So to find our eigenvalues, we set that equal to 0 and factor. So our characteristic equation tells us that 0 is going to equal to that characteristic polynomial, which is lambda minus 5 times lambda plus 2. So our eigenvalues are going to be 5 and -2. Okay, so step 1 complete. We have found our eigenvalues. Now we want to find our linearly independent eigenvectors, and we're going to do this by taking basis vectors for each eigenspace. So let's start off with maybe lambda equals 5 and find the eigenspace for that. We did this in more detail in the last video, so if you need a refresher, you can go ahead and look at that. Okay, so lambda equals 5, we go ahead and take our our A minus lambda I and plug in 5 for lambda. So this would be -3, 3, 4, -4. And we look at the corresponding homogeneous system. And we can row reduce this. This would become 1 minus 1, 0, and 0, 0, 0. So then our eigenspace is going to be the null space that corresponds to this system, which if we look at all the solutions of this homogeneous system, this is x1 equals x2, and x2 is a free variable, so it also equals x2. So this is going to become x2 times the vector 1, 1. And in particular, this is the entire thing is our eigenspace, but this vector right here, this is going to be our basis vector for our eigenspace. Okay. Now let's do the same thing for lambda equals to -2. So we're going to take our a minus lambda, so this is 2 minus 2 is 0. Oh wait, sorry, 2 minus minus 2. All right, 2 minus minus 2, this would be 4. 4, 3, and 4, and 1 minus minus 2 is going to be 3. All right, so here's our homogeneous system. And we can simplify this down to get 1 3/4 0 0 0 0. Okay, so that means our basis vector for this is going to be the vector, well, 1 is -3/4 x2, x1 is -3/4 x2, and x2 is a free variable, so it's just itself, it's just 1. So here's our basis vector. Okay, so step 2 complete. Now for step 3, we want to find p. So p, we're going to take each of our basis vectors and just plot them in. So our first column we'll put 1, 1, and our second column we'll put -3/4 1. And then for our d, we want to put the eigenvector or eigenvalues on the diagonal, and we want to put them in the order that we put it in P. So our first column in P corresponded to lambda equals 5. So our first column in D should also be lambda equals 5. And then our second column in P corresponded to lambda equals -2. So our second column in D should also correspond to that. There we go. So there's our P and our D. So our factorization would be P dP inverse. Okay. Let's try one more example. So this is problem 8 from section 5.3, and this asks us to diagonalize a equals 5, 1, 0, 5. So let's start off again with finding the eigenvalues. And the eigenvalues here are easy to find because this is a triangular matrix. So the eigenvalues are 5. Well, there's only one eigenvalue, but it has multiplicity 2. So now let's find our eigenspace for this. So if we do this, we're going to take a minus lambda I, and here lambda is 5, so this will give us a 0, 1, 0, 0. And we look at this homogeneous system, and we want to know what the basis for this is. Well, the basis for this, it's already in reduced form. So we've got our eigenspace is going to be x1, x2, and x1 in this case is our free variable, and x2 is 0. So our eigenspace is x1 times 1, 0. Okay. What this means is our basis for our eigenspace is going to be this 1, 0. But this is a problem because this is one linearly independent eigenvector, not 2. So our problem here is that in order for this to actually work, we need to have 2 linearly independent eigenvectors. But we only have one. What does this mean? This means that A is not diagonalizable. Incidentally, we know that we can't find a second linearly independent eigenvector because there are no more eigenvalues to draw from. So A is not always going to be diagonalizable, but we have a couple of shortcuts to tell. One is this theorem: if A is an n by n matrix with n distinct eigenvalues, so if all of the eigenvalues are different, then it will definitely be diagonalizable. And this makes sense because every eigenspace is going to have dimension at least 1. So if I have n different eigenvalues, then I will have n different one-dimensional spaces. So that will add up to n linearly independent eigenvectors. An important thing to note is that if we have matrices with eigenvalues that aren't distinct, they can still be diagonalizable. So looking at problem 8, when we got to the point where we said, well, we have only one eigenvalue, which is 5, but it has multiplicity 2, that wasn't enough to tell us it wasn't diagonalizable. Oh boy. Sorry, this is supposed to be A is not diagonalizable, not A is not eigenvectors. A is not diagonalizable. This is what happens when you try to write and talk at the same time. Okay, so A is not diagonalizable. So in problem 8, once we saw that one of our eigenvalues had multiplicity 2, that wasn't enough to tell us it wasn't diagonalizable. We had to go through the whole thing and see that we didn't have linearly independent eigenvectors. Okay. So to recap, we saw that if we can diagonalize A, then we can shortcut a lot of our processes. For instance, raising to a power or finding eigenvalues and eigenvectors. And then we saw how do we go about diagonalizing A.